Welcome to this explainer. All right, today we're rolling up our sleeves and stripping Kubernetes down to its absolute bare metal. We're going on a bit of a journey, starting from the foundational definitions and working our way all the way up to advanced cloud scaling. We're looking at the core building blocks that make true cloud-native architecture actually work. So when engineers first start getting their hands dirty with Kubernetes, they almost always make one huge fundamental assumption. They think the absolute baseline, the smallest deployable unit in the system, is a container. And honestly, logically, that kind of makes sense, right? Containers are the things packaging our applications. But is that really how Kubernetes operates under the hood?
Well, it turns out that is completely false. No way. And wrapping your head around this is a massive paradigm shift. The smallest deployable unit in Kubernetes is actually not the container at all. It's the pod. Unlocking exactly why this is true sets up literally everything you need to know about mastering Kubernetes and, more importantly, avoiding those dreaded 3 a.m. pager alerts.
Real quick, here's our roadmap for today's session. First, we'll cover the smallest deployable unit. Then we'll peek inside the pod architecture itself. After that, we'll tackle lifecycle, networking, and storage, move into scaling and cloud environments, and finally wrap up with some hard-hitting best practices for architects. Okay, let's dive right into Section 1, the smallest deployable unit. So this begs a really big, logical question. If containers are the things actually running our applications, why on earth does Kubernetes deploy pods instead of just deploying the individual containers directly? Like, why add a whole other layer of abstraction? To understand that, think of a pod as a wrapper. It's a wrapper around one or more containers that are deployed together as a package deal. Because they live inside this shared wrapper, they share a network namespace, meaning they get the exact same IP address. They share storage volumes, a hostname, Linux namespaces, and a lifecycle. The absolute critical takeaway here is that Kubernetes schedules and manages pods. It does not manage individual containers. Without this pod wrapper, Kubernetes simply couldn't coordinate complex workloads efficiently across a massive, sprawling cluster. Moving right along to Section 2, inside the pod architecture. Let's look at how these things are actually built. Look, let's not overcomplicate things. The vast majority of your workloads are going to be simple, single-container pods. We're talking about your standard web APIs, microservices, background workers, REST services, event processors, the usual suspects. Sticking to one container per pod keeps your application architecture incredibly simple, while still letting Kubernetes manage the lifecycle of that entire unit completely independently.
But what happens when you actually do need more than one container? Well, that's where tightly coupled multi-container pods come into play. Sometimes your main app just needs a helper process, a sidekick. You might have a logging sidecar, like FluentBit, grabbing and forwarding application logs. Or maybe a service mesh, like an Istio Envoy proxy, jumping in to manage encryption and traffic. You could have a monitoring agent exporting metrics, or a config helper watching for reloads. Because these sidecars run inside the exact same pod as your primary app, they share that network namespace we talked about, so they can talk to each other seamlessly right over localhost. They operate as one single cohesive unit.
All right, Section 3, lifecycle, networking, and storage. This is where things get really dynamic. A pod goes through 5 distinct lifecycle stages: pending, running, succeeded, failed, and terminating. But here is the crucial thing you've got to remember. Pods are inherently temporary. They are completely ephemeral. If a pod crashes and hits that failed state, Kubernetes does not repair it. Let me say that again for emphasis. It does not fix a broken pod. Instead, it creates a brand new one to replace it entirely. This is an absolutely foundational principle of cloud-native architecture. So, if pods are constantly dying and being replaced, how do we handle shared resources without losing our minds? Well, every pod gets a unique IP address and can talk directly to other pods. But since that IP is going to change the second a pod dies and gets replaced, your networking and storage have to be decoupled from the pod itself. To handle data, pods hook into volumes for shared storage. Things like empty-dir, persistent volumes, PVCs, config maps, and secrets. These volumes persist based on their own specific configurations rather than relying on the short, fleeting lifespan of the pod. Let's move to Section 4, scaling in cloud environments. This is where the magic really happens. To really grasp this, we need to completely reframe our mental model. On one hand, you have traditional IT infrastructure. This old-school model treated servers as long-lived permanent assets. You gave them cute names, and you carefully fixed them when they broke. On the other hand, we have cloud-native infrastructure. This model treats pods as temporary, completely disposable execution units. You do not patch a broken pod, you destroy it, and you let Kubernetes spin up a fresh one. This massive shift from manual server repair to automatic, ruthless self-healing is an absolute game changer for minimizing downtime and saving on cloud costs.
So let's see how this plays out during real-world scaling on managed platforms, Google Kubernetes Engine, Azure AKS, or Amazon EKS. Imagine traffic suddenly spikes. A Kubernetes deployment automatically creates additional pods. Each new pod instantly and seamlessly receives its own unique IP, its sidecar proxy, shared secret and config map volumes, and all its monitoring integrations. Boom. The end users experience perfectly smooth scaling without ever having a clue that entirely new pods were dynamically provisioned in the background to handle their requests. Finally, Section 5, Best Practices for Architects. How do we actually build for this?
First, let's talk about what not to do. There are some very common, frequent operational blunders that will absolutely tank your application's scalability and resilience. Things like storing application state directly inside the pods, hard coding or depending on specific pod IP addresses, trying to SSH into a pod for manual administration, assuming a pod is permanent, or cramming totally unrelated applications into the exact same pod. Honestly, if you do these things, you are fighting against the very DNA of how Kubernetes was designed to work. To avoid those anti-patterns, we have to adopt some strict design rules. The best practices are super clear. Always prefer one application container per pod. Keep your pods entirely stateless whenever humanly possible. Push that persistent data out to managed databases or external persistent volumes. Always use Kubernetes services for communication instead of relying on those temporary pod IPs. And please, always configure your readiness and liveness probes. Stateless design is the exact secret sauce that enables Kubernetes to scale, recover, and operate your workloads automatically.
To wrap this all up, there is one powerful rule of thumb you need to carry with you. Design your application so losing a pod is an expected event, not an outage. If you can truly embrace this model and treat your pods as the disposable execution units they were meant to be, your cloud-native architecture becomes practically unstoppable. So, I'll leave you with this final provocative question. Is your current application truly ready to lose a pod right now, this very second, without a single user ever noticing? Think about it. Thanks for joining this explainer, and keep building resilient systems.